guys, welcome to the next session of solutions. In this session we will be discussing about vapor pressure, but in this time we will be studying about solids which are present inside liquids. So let's start the session. So as I said, we will be studying about vapor pressure of solutions, but this time solids inside liquid. Now let me explain what happens. Okay, so this here is a diagram of a pure solvent. So whenever there is a pure solvent, consider these are the atoms, or let's say the molecules which are present. So the same molecules are present in the atmosphere. Okay, so they escape out in the atmosphere. Now for example, if you add a solid, okay, so if you add some solid, like here there is 1 mole of solvent and 1 mole of solute. Okay, so this is, you can see, solvent which is present in larger quantity, and this is your solute particle which is present in small quantity. So obviously here we are talking about solids in liquid. That means the solute particle are the solid. So obviously solids do not go in vapor phase. So you can see that the vapor pressure here is getting reduced. Now I will explain this graphically also. Okay, so just note that the number of molecules in the vapor phase are less. Okay, so the vapor pressure is getting reduced whenever there are solids in liquid. Now going in detail, this here is the explanation, okay, of the previous diagram. If you guys want, you can pause the video and you can read out. Okay, now what happens actually, this was the graph that we were studying according to our Raoult's law. So again, Raoult's law is what? For any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. So if you see, this was the equation. Okay, let's say that we have a binary component, that is binary solution, that is let's say 1 is your solvent and 2 is your solute. So P1, that is the partial pressure due to 1, is proportional to x1. So because only x1 is allowed to go in the vapor phase, so we see that partial pressure is equals to P1 not x1. So if you see here in this figure here, that this is going to be the vapor pressure of the pure solvent. Okay, that this is the of the pure solvent and this is of the mixture. So let's say that this is the mole fraction of the solvent. So as the mole fraction goes from 0 to 1, you see the pressure is increasing. Let's say originally this was the scenario where you had the pure solvent. Now if you add some solid particle, what will happen? The mole fraction will not be 1, it will decrease. Let's say the mole fraction is approximately 0.8. Okay, so you see the vapor pressure that is generated is little bit less. So you can say, like, generally that vapor pressure of solution decreases when you are adding a non-volatile solute inside the solution. Is it clear? Okay, so very important, please understand this very carefully, otherwise just rewind 1 minute back and re-watch this part. Okay, so going ahead, there is something which is called as ideal solution. Now ideal solutions are those solutions which obey Raoult's law over the entire range of concentration. Okay, so these are your ideal solution. Now there are some properties related to the ideal solution. So first property is that the enthalpy of mixing of pure component to form the solution is 0, that is delta H of mixture is equals to 0. Okay, the volume of mixing is also 0, that means the change in volume delta V mix is also 0. Meaning of this is actually no heat is absorbed or evolved when the components are mixed. This is the first point. Okay, so no heat is absorbed or evolved when the components are mixed. Second one is telling the volume of the solution would be equal to the sum of the volume of the two components. For example, let's say that you have 100 ml of A and you have 100 ml of B. If you mix the two, you get a final volume as 200. Technically they should not react with each other. If they don't do that, then only we say that these are ideal solution. So the answer, like what is an ideal solution, basically what happens is, let's say that you have component A and B which you are mixing. So the answer lies between the molecular interactions. So let's say that A will interact with A, right, because there is this force. B will interact with B and A will also interact with B, or you can say B will interact with A. Okay, vice versa. So These are the three forces. Now, if the intermolecular forces of AA and BB are almost equal to, or let's say nearly equals to AB interaction, then the solution is actually an ideal solution. Example, N-hexane and N-heptane. Another example is bromoethane and chloroethane. And one more example, benzene with toluene. So you can have many more examples. So important here is the interaction between AA and BB should be having same amount of intermolecular attractive forces as that of AB or BA. Okay. Now, talking about non-ideal solution. So obviously these will be the solution which do not obey Raoult's law over the entire range of concentration. So they will be called as non-ideal solution. Now these are of two types. One is called as positive deviation. So you can see first is positive deviation and then there is another negative deviation. Now positive deviation means the partial pressure is more. Okay, so partial pressure in these cases higher than what is predicted from Raoult's law. Now, why is the what's the reason behind this? The reason is that AB interaction are actually weaker. So if you mix liquid A with liquid B, okay, so what happens? Like the interactions are weaker, so the molecule tend to stay in AA or BB form. That means they are much more comfortable to escape outside and stay in the gaseous state. Okay, very important that they are actually trying to stay in the gaseous state. So in such solutions, molecules of A or B will find it easier to escape in pure state, that is in the gaseous state. That's why this will increase the vapor pressure and results in positive deviation. Examples are very important from exam point of view: ethanol and acetone mixture, carbon disulfide and acetone mixture. Now this was about positive. Now let's look at negative deviation. So it is kind of vice versa, it is opposite. Here in the positive deviation we saw that AB interactions are weaker. In case of negative deviation, AA interaction and BB interaction are weaker. Okay, so what is happening, like the molecule are staying in AB form, that means they are staying inside the liquid form. So this tends to decrease in the vapor pressure. Example is phenol and aniline, or the other example is chloroform with acetone. Now just to show the graph of this deviation is this one. The green line here represents the ideal behavior. Okay, this is the one that is predicted from Raoult's law. So if you see here, the vapor pressure of the solution is higher. Okay, the vapor pressure is higher. So this behavior is actually telling it's a positive deviation. When the vapor pressure of the solution is higher than the predicted value, it is a positive deviation. And this here is again your Raoult's law, predicted by Raoult's law, and actually by experimentation we see this is the violet curve, which is actually lower vapor pressure. So this is actually a negative deviation from Raoult's law. Okay, so please understand both of these graphs. In general, the numericals are not numerical. The questions are asked based on positive and negative deviation. Okay, now one more thing that you should focus on, that is azeotropes. Okay, like for example, some of the liquids, when you mix them together, they form azeotrope. What is an azeotrope? They are actually binary mixture which have the same composition in liquid and in vapor phase and boil at constant temperature. Okay, so they have the same composition in liquid and same composition in vapor phase. So there are two types of azeotrope. One is minimum boiling azeotrope and the other is maximum boiling azeotrope. Okay. So the solution with large positive deviations from Raoult's law form minimum boiling azeotrope at specific composition. Okay. Same way, solutions with large negative deviation from Raoult's law form maximum boiling azeotrope at specific composition. Now, in order to explain this part, okay, how to memorize or remember this statement, like solutions are having large positive deviation. Now let's go back. So if you see here, the positive deviation is quite large. Okay, so whenever the positive deviation is large, that means the components are volatile. Volatile meaning they will evaporate much more faster, right? So obviously they need less temperature to vaporize. Okay, so that's why whenever there is large positive deviation, minimum boiling point will be observed. So minimum boiling point, and same way you can see that for negative deviation is this one. So you see that the vapor pressure is quite low. Okay, if vapor pressure is low, that means you need much more higher temperature to achieve the atmospheric pressure. Okay, this I will explain in one of the topic, how is, like, what's the definition of boiling point. So there you will understand. Actually in this one next session you will see the new definition of boiling point. Okay, to understand this point, this here vapor pressure requires more amount of temperature achieve the atmospheric pressure, and only then it will boil. So that means a large negative deviation from Raoult's law will show maximum boiling azeotrope. One example is a mixture of nitric acid 68% by mass and water 32% by mass, okay, with a boiling point of 393.5 Kelvin. Okay guys, thanks a lot for this session. I hope you guys enjoyed this one. Thank you. See you for the next one. Bye bye.